We are videotaping for our absentees. Today is what, the 16th? 116. So if you were absent on 116, then this is for you. So, all right. Let's look. We're just going to review for those who were absent yesterday and do one torque problem so that you can sort of be up to speed for what we're doing the rest of the day. So, again, this mod has come along and been very strange in that it seems like the topics aren't related to one another. We were hanging pictures with tensions we had to calculate, then we went on the elevator and we had to look at what was happening to the apparent weight on the scale as we went up and down. Then we switched to, what was it before torque? What was it? No, that's now. I guess it was the elevator right before this. All right, so now we're on torque. So this is like, it seems like they're unrelated, but there's one thing that dominates. Newton's second law, sum of the forces equals ma. And we learned yesterday a new force, and you weren't here, you two, to hear about it. And this force causes rotational movement. And when you get to the video, there's a bunch of definitions that I can't go over right now, but you can jot them down then. I don't know about you, Alex. Someone in your house might have to jot them down for you. So there are torque problems, and the sum of the forces equals ma is tweaked a little bit. It becomes the sum of the torques equals ma. And torques, again, is the force that causes rotational motion. So that's just a very, very broad summary of what we did yesterday. All right, to go on, let's do a torque problem, and some of the principles will show up as we do it. In your comp books, then, who's going to write very neatly for Alex? Morgan, you're pretty good at that. All right, so remember we have a still stick. So draw yourself a still stick. A stick that is still is in what kind of equilibrium? Brendan, do you recall the name for that?
Static.
Right. Static rotational equilibrium. This one is also in static translational equilibrium, and that just means it's still, all that. So we have a still stick, and we came along and we thought, what if we set it on a fulcrum? A fulcrum is a balancing point. What have we created? This was probably what brought up to mind my prayer cue. What is this? Seesaw. The seesaw. So those things are vicious. Remember? You can get really hurt on those. You notice they're not in playgrounds anymore. Unless they're on the springs, you know. And then
I think those are stupid.
Alex?
Short story.
Yeah, sure.
One time I was on a seesaw with my sister, my older sister, and she went down really hard.
Yeah.
I went flying up in the air, and I came back down, and the handle was metal, and I hit my chin on it, and my chin ended up falling off, basically.
Oh my, you had to.
So I have a scar right here. It's the skin. It all just kind of fell off.
Well, I told you, they're vicious.
They are.
Especially as a little child and you don't know about torque yet.
Like how babies, if you shake them too much, they'll actually like die.
Yeah.
It's like that, except with a toddler.
Yeah.
And much faster.
And we put these things in the playgrounds. Like, where was our minds, you know? So, anyway.
See, I think about it.
All
If you
right.
shrink babies too much, they just die.
It's true.
Yeah, because their necks are so
Yeah,
long.
'cause
No, I think it's the brain. It's the brain, I think. All right.
Yeah, they're bobbleheads.
And
And
then
you shake them too
soft
much.
heads.
Like a
Oh,
lady at my mom's
it's
work
the-
did that, and actually.
There is something in the brain that gets, the brain gets damaged.
Because you know you're
actually.
playing with them, and then actually she didn't do it. The daycare girl did it.
Or playing.
No, like when you.
You're having fun.
All right, sorry, Jonathan. All right. All right, back to the seesaw and the vicious seesaw. I want you to put a spot A on this side, a spot B on this side, and a spot C on that side. About at the same spots that I have. And now I would like to indicate that the person sitting on A has a weight of 8 newtons. And recall, if when you decide whether that's a positive torque or a negative torque, you pretend these guys aren't on it. So what kind of rotation would this cause if this was the only guy? What kind of vicious rotation would it cause? You don't want to be the only one on a seesaw. All right, it goes like that. And what did we decide? Was that positive or negative? All right, we decided counterclockwise rotational motion is negative. So this guy over here, B, is, oh yeah, we need to know where this guy is first. So this guy is 2.5 meters from the fulcrum. And then we have point B is 0.5 meters from the fulcrum on this side. And the distance between B and C is 1.3. So that's not from the fulcrum, which we will have to calculate, a small calculation there. The only other thing I know is the weight of this guy, and it's 3 newtons. And guess what the question is going to be? Can you foresee? What is the question going to be? Find what? Find weight of B. B weight. I'll call it W, weight of B instead. Because B could be where it's sitting. We know that. I'll say weight of B. That's my symbol. All right. So yesterday, and this creates a positive torque, and so does this guy, positive torque. If they were the only ones on it, do you see the rotation would be in a positive direction? All right. So this is our dominating formula. Let me move that up and make some space to write. Are we supposed to have visitors today?
Even when we're supposed to have visitors, they just don't come.
Someone from the church, this church, not Good Shepherd, but NCCS.
Like elders.
I might have been elders, but I'm not sure. All right.
So into
Have anyone seen anybody in the halls? No? Okay. Sum of the torques equals MA is what we're going to do. So how many torques are created by this scenario? So how many torques are there in this problem? Hannah?
Is it just 3?
There are 3. This one creates a torque, this one, and this one. So how do you know there's a torque? Because there is some rotation. So we're going to say torque of A, whatever he creates, plus torque of B, whatever he creates, plus torque of C, equals MA. Now, I want you to find the weight of B so that this is in equilibrium. So let me add that to the question. Find the weight of B so the stick is in equilibrium. The seesaw is in equilibrium. And we'll call it static equilibrium. So in other words, that's all fancy to say it's still. So, but we're in physics class. We're not going to use words like still. We're going to call it static equilibrium. All right. So, all we have to do is fill in the numbers. One thing will be absent, and that'll be the weight of B. So, torque was made of 2 things. So, Aaron and Alex, torque is force perpendicular times R. And we're going to set that up at each spot. So force perpendicular times R for the A guy plus force perpendicular times R for the B guy, and the same for the C guy. So we need to fill in. I'm going slow. So normally we would jump right from this step to the step I'm going to write now, but I'm just showing those who are absent what our thinking is. All right, what is the force on the A guy? Annabella, your name starts with A, so tell me about the A guy. What's the force that he is bringing to the picture? 8. 8.